Cool. And yeah, so the last speaker of the session and the last speaker of the day is Zhuoran Yang, and he's going to be talking about sequential information design. So let's, yeah, again, I'll let you take it away if you're ready to go.
Yeah.
Great.
Thank you, Dylan, for the introduction, and thank you for the invitation. It's my great pleasure to be here. And today I'm going to talk about our recent work on information design, or in other words, Bayesian persuasion. And this is joint work with Jibang Wu, who is a PhD student at Virginia, and Zhuoran, who is an undergrad at USTC, and Zhe from Google, and Zhuoran from Northwestern, and Mike Jordan from Berkeley, and Haifeng from Virginia. And my talk will be divided into 3 parts. I will first talk about briefly motivate the problem, and then I will talk about our new model, which is called Markov Persuasion Process, and which is a model about sequential version of Bayesian persuasion. And finally, I will introduce the algorithm for solving this problem when we don't know the model and need to estimate, learn how to persuade in an online fashion from data. So first, I will talk about the simplified motivating example. Just consider a ride-hailing system where a customer P wants to take a ride, and she is in a remote area, let's say at Berkeley Hill, and then this is he's in the mountain, and there are no available drivers nearby, and then to serve this customer, the platform would like to encourage available drivers in distant areas, say in San Francisco, to come to Berkeley to pick her up. But that available driver might prefer to stay at San Francisco because there might be more opportunities, and that driver might be willing to wait for a bit, even if she is available right now. She might prefer to wait at San Francisco for other customers and serve them. So the only way that we can, the platform can incentivize this driver to drive all the way from San Francisco to Berkeley Hill to pick up that passenger, is say to give that driver a better pay, say getting a better tip. Then this simplified example assumes that the customer, the passenger are divided into two types. One type is called good tipper, who are very generous about tipping. And another type is called bad tipper, who are not. Then the driver is we assume that the driver is only willing to come all the way from San Francisco to Berkeley if the driver, if the passenger is a good tipper. Now, for this setting, the driver and the platform have misaligned objectives. For the driver, she wants to have good tips, so she only wants to come to Berkeley to pick up the passenger if she gets good tip. But for the platform, the platform wants to serve the passenger because the platform is essentially a matchmaker, and the platform gets service fee if the passenger and the driver are matched. Then for this problem, there's an information advantage because the platform knows exactly whether P is good or bad tipper, but the driver only have a prior distribution about the type of the passenger. And for simplicity, we assume that the prior probability of a good tipper is one third, and the bad tipper is 2/3. Then the platform might be sending a signal to incentivize the driver to come to Berkeley and pick up the passenger. And the signal here we assume is just a rating, say rate the passenger as a good tipper or bad tipper. And the platform might be able to send such a signal to the driver in order to maximize the platform's utility, which is the probability that the driver and the passenger are matched. Or in other words, the driver comes to Berkeley to pick up the passenger. Then how do we signal a rational driver? There are a few strategies. The first one is to always signal good. or always signal bad. It makes no difference. Then such a signal has no information, because if the driver computes the posterior is equal to the prior, then based on the prior distribution in our previous slide, here the probability that the bad tipper is larger than the probability of good tipper, then based on this prior, which is equal to the posterior, the driver will not come. So in other words, there's no service. So the utility for the platform is 0. Now consider a second strategy, which in which the platform truthfully reports the type of the customer. That is, if the customer is indeed a good tipper, then the signal is G. Otherwise, the signal is B. Then, from the perspective of the driver, the optimal way is to just follow directly the signal. That is, if the driver sees G, then she will come to Berkeley and pick up, and otherwise she will just stay at San Francisco and choose not to pick up. Then the utility is just equal to 1/3. So is it possible that we can do better? Actually, there is a way to do better. That is to send noisy information, or we can randomize the signal. Let's suppose we send signal in this fashion. This GT means good tipper, BT means bad tipper. And I have a figure showing this policy. Yeah.
Sorry, so when you talk about doing better, you mean doing better from the platform's perspective at the driver's expense, right? So the driver is going to end up being exploited by Uber to more frequently pick up people who don't tip it, right?
Not necessarily, because it might also benefit the driver, because the driver might have better tips. And
is that changing the example, or does that happen in any example? I don't understand. It seems like if the driver knows that the person is not a tipper, that it's just forced with it, right?
So sorry.
Is there a driver optimal thing that, like on the previous slide where you say always report the symbol?
So the driver doesn't know exactly what the passenger is.
Slide?
Yeah.
Isn't strategy 2 optimal for the driver?
Optimal for the driver. It is optimal for the driver, given the signaling scheme. Because when you compute the posterior distribution, it turns out that following the signal is optimal for the driver.
Is there any other scheme that the driver would like better than this one?
I'm not sure.
No, you cannot do better than perfect team. That's perfect measure. That's the best of all possible worlds for the driver.
So just when you say, can we do better? I'm asking, it's can you do better from the Uber's perspective, and the only way that can happen is to do
so you're trading off driver's utility with driver's utility with consumer utility. They're doing this, yes.
So it's do better for the from the perspective of the platform.
But it depends on the platform objective. So if the platform is all about pleasing drivers, then full information it's bad. But maybe the platform is trying to balance, strike a balance between the interests of these two groups, and then in that case, you might want to, please more the customers and less the drivers.
Yeah, fair enough. I wasn't trying to get into a debate. I was just trying to understand what the notion of better meant.
So here, the platform's goal is to maximize the probability of the service. This is the utility. I think it's in.
Well, in an example, that might not be like ex post individual rational for the driver. Like the driver is going to be sort of happy on expectation, but like a lot of the time in the realization, they're gonna think it's worth it.
Yes, exactly. Because the driver doesn't know whether P is good or bad.
Yeah.
This is the information asymmetry.
Thank you.
So can we do better? What I mean is, can the platform do better, achieving a higher utility than 1/3 or half? And it turns out that sending a randomized signal is better from the perspective of platform. let's say if the platform knows exactly P whether P is a good tipper or bad tipper. So if P is good tipper, then the platform will always signal G. And otherwise, with probability slightly smaller than 1/2, it will signal G, and with probability slightly above 1/2, it will signal B. And this is given by this figure. Then given this, we can compute the posterior distribution upon receiving a signal, whether it's G or B. So if the signal is G, then the posterior distribution for a good tipper is actually slightly above 1/2. And so given conditioning on the signal G, the posterior distribution of the bad tipper is slightly below 1/2. In other words, if the driver sees a signal G, then it's actually better off for the driver to pick up the passenger, because it has a better posterior utility from the perspective of the driver. Then, in other words, this driver takes order if and only if this condition holds. But if the driver sees signal B, then definitely the driver knows that it's a bad tipper, so she will not come. And so for this signaling scheme, the optimal policy for the driver is to always take the order if she sees the signal G. Then with this signaling scheme, the utility is equal to the probability of signaling a signal G shows up in the system, which is about 1/3, about 2/3. So 1/3 of this probability comes from this channel, and the other one about 1/3 comes from this channel. So the probability of P being a bad tipper is about 2/3, and with about 1/2 probability with signal G. So this channel offers another about 2/3 probability. So in other words, with this randomized signaling scheme, the platform achieves better performance. And this example shows the power of persuasion. So what does persuasion mean? Persuasion means the act of exploiting an information advantage in order to influence the decision of others. Here, the informational advantage lies in the hand of the platform. The platform knows exactly what the type of P, but the driver only knows the prior distribution. And persuasion is ubiquitous in everyday life. As the title of a paper in American Economic Review says that 1/4 of the GDP is persuasion. And there are many real-life examples, including cybersecurity, negotiation, and regulation, etc. And the mathematical model we consider of persuasion is called Bayesian Persuasion. It's pioneered by this famous paper. And Bayesian Persuasion is a static game played between two players. One is called the sender, and the other one is called the receiver. So sender here is just a platform. Receiver is a driver which receives the signal. And sender observes the outcome from a prior distribution. Here, this outcome is whether P is a bad tipper or a good tipper. And the prior distribution is just 1/3 or 2/3. And upon observing an outcome, the sender will send a signal to the driver, and then to the receiver. The receiver receives the signal and computes a posterior distribution about the outcome. Then the receiver will take optimal, will be rational in the sense that it will choose the action which maximizes the posterior expected utility. Here, U is the utility of the receiver, and this expectation is equal to the posterior expected value of the utility function if action A prime is taken. Then the receiver will choose the action which maximizes this quantity. then the sender's return is given by the expected expected reward. So here, sender has another reward function, which might be different from the utility function of the receiver, and this is the expected value, expected reward obtained by the sender, and it depends both on the prior distribution and implicitly depends on the signaling policy. Here, I say it implicitly depends on that because the sender cannot take the action. The action is taken by the receiver. And the goal of Bayesian persuasion is for the sender to choose a signaling policy which maximizes the sender's objective. And here, our goal is to extend Bayesian persuasion to the sequential setting, because the classical Bayesian persuasion is a static game. We want to also consider sequential changes, and which is motivated by real ride-hailing systems where there are some seasonal changes and also changes in demand and supply through time. And also, we would like to design a probably efficient reinforced learning algorithm for solving this. And the model we consider is called the Markov Persuasion Process, which involves a sender and a group of myopic receivers. And at each time, and those receivers joins the game sequentially. So at each time, a new receiver joins the game and plays a Bayesian persuasion problem with the sender. And in specific, the sender receives the sender observes the outcome and sends a signal to the receiver. And this receiver receives this signal and takes a myopically rational action. And then after taking that action, the receiver gets the immediate reward and leaves the system. And then upon taking that action, the system evolves into a new state according to a Markov transition kernel. And the goal of the sender is to design a signaling policy which maximizes the cumulative return obtained by the sender. Oh, myopic means that upon the optimization problem is exactly characterized by this. So that means there might be multiple receivers, but the receiver only look at the utility at its current steps, at the current steps time step. And after taking that action, that receiver leaves the problem, leaves the system, and the next step, there's another new receiver comes to the system.
That's the rational thing to do. So this receiver is very rational, right? So conditional in the information that it's got is doing the best for itself. Mm-hmm. But you mean myopic in the sense that it's ignoring its impact on.
It is ignoring the past receivers. That is, the receiver today doesn't have no knowledge about receivers yesterday, and
so is the distribution of actions or signal realization in the past informative to that? Are they signal independent, or what's the information?
Oh. So the signaling are not independent. It depends on the underlying state and the outcome. The outcome, we assume that this mu are independent.
So the state stays fixed over time. Is that the assumption? There is a fixed state, and so observing more signals is telling me something about the state.
Yes. Well, yes and no. I will talk about the exact definition in a later slide. And also for learning, we consider this online setting where we want to learn from interaction. And for that, we need to, by interacting with the environment, the goal is to collect a good data set for exploration. And like many other online learning problems, we need to deal with the trade-off between exploration and exploitation. And now, yeah.
Going back to your introduction example with the share rights, how does the myopic behavior relate here?
Oh, here is static. This game is static. It's not myopic. It's not a sequential problem. So that means you can for this problem in the signaling this strategy 3, if you are taking action according to this, you are automatically myopic irrational because you only look at the utility at the current step. This is what I mean by myopic.
Can you give us an example of your more general setup that's big?
Oh, yes. So consider, say, the platform wants to maximize the revenue or the revenue in a total month, in a whole month, and within each day or within each week, the demand and supply might oscillate, and also the demand and supply might depend on some contextual information. Like, for example, if it's a national holiday, then perhaps the demand is increasing.
So how is all of that showing up in your omegas? Signals and
I will talk about this formulation in the in this the mathematical model is here. So we consider there are a few variables. This S is called state, and which is affected by the action. And also there's a outcome which sampled from the prior distribution. And at each step, the receiver and the sender both observe the current state of the system, and the sender observes the exact value of the outcome, but the receiver only knows the prior distribution. And then the sender sends a signal, the receiver takes an action, and the state evolves into a new state according to a Markov transition kernel. But this omega, this outcome, it's not affected by the action. So intuitively, this can be viewed as some random process or some seasonal effect which is not affected by the action of the receiver. And so here, what I mean is by myopic irrational action, what I mean is the receiver observes the current state and receives the signal M, then it computes a posterior distribution and chooses the action which maximizes the immediate reward. The immediate utility. I forgot this immediate utility U, which is the same as in the example. Yeah.
so why do you need to introduce the outcome apart from the state in this model?
Oh, the reason is if the state is
Why can't it be that the sender knows the state, but the receiver does not?
if the sender knows the state, but the receiver doesn't know this. Well, how do I do this? Then it will become a different model. It will become a partially observable MPP, and the receiver needs to infer a belief state, infer the distribution of the underlying state. It's a different problem. Here we consider, in some sense, an easier problem, because if it's a pump DP, here the sender cannot take the action, then exploration will be very hard. And here, in our setup, there's again information advantage in the sense that the sender knows exactly what the outcome omega is, but the receiver doesn't know. And there's a misaligned objective. Each receiver joining the game wants to maximize the immediate reward, immediate utility U, but the sender wants to maximize the cumulative. That is, we assume there are capital H number of steps. We consider episodic case. And the goal of the sender is to find a signaling scheme which maximizes the cumulative return. And for this problem, there are a few challenges. Well, the most important challenge is the couple challenge due to exploration in an online setting and the constraint due to Bayesian persuasion. That is, we want to ensure that the the signaling, we want to ensure that the signaling scheme satisfy the constraint due to Bayesian persuasion. That is, the action taken by the receiver is posterior optimal. Then there are two questions, two additional challenges compared to standard MDP due to this persuasiveness. The first one is, how do we come up with an exploration incentive that is subject to persuasiveness? That is, when we want to do exploration, because the sender is not taking the action is determined by the receiver, but still we need to explore the system. Then how do we do this exploration? And the second question is, when there's a persuasiveness constraint, how do we maximize the policy? And here, this objective depends on the reward in a sequence in a whole episode. So it's the sum of H reward functions, and we want to maximize this cumulative return. And in the interest of time, I will skip the related work. So for this problem, if we know I need to mention that what do we know? And so for online learning, by saying online learning, we want to design the policy for the sender. And from the perspective of sender only observes the state, outcome, and action reward. And the sender knows the utility of the receiver because it needs to compute the best response of the receiver. But the sender doesn't know the state, the reward function of sender itself, and it doesn't know the state transition. And this is very important because if it doesn't know the state transition, it needs to explore. And it needs to explore by incentivizing the sender to take correct actions to explore the system. And if we know the model, then we are able to characterize the optimal solution. For this problem, there's a revelation principle type of result showing that although you can send arbitrary signal, it suffices to just send the signal which lies in the action space. That is, you can treat your signal as a recommended action. And then given that, by saying that the policy is the class of policy that is admissible is that the policy is incentivized. It's called persuasiveness. That is, the policy, the action recommended by the sender is indeed posterior optimal. This is given by this complicated equation, but here what this term is that this A is the recommended action, and it's the posterior expected returns following this recommended action, and it's better than when you are recommended by A but taking action A prime. That means always following, given this condition holds, then always following the recommendation is optimal for the receiver. Then the optimal policy can be characterized by the greedy function, greedy policy with respect to the action value function. Here, this action value function satisfies this Bellman equation, which is very similar to the classical one. But the only difference is that here, taking the greedy policy should be taken within the set of persuasive policy. It depends on both the prior distribution and the utility function. And for now, I would like to briefly talk about this online setting for the problem we are interested in for the sender. So in terms of online learning, from the perspective of sender, it just specifies a signaling policy and recommend it to the receiver and collect the new data. In the data, the action is taken by the receiver. But when the policy is persuasive, then we can ensure that this action is exactly sampled from the policy. And we assume that there are T episodes. And to characterize the performance of the algorithm, we use the standard notion of regret. And in addition to regret, we also need to ensure persuasiveness. So that is, we want to ensure that the pi t is always persuasive with respect to the prior distribution, and the utility function. Here, the prior distribution is not known to the sender, but the sender is only able to collect a sample from the prior distribution. Then, compared to classical reinforcement learning, the only the main additional stuff is this persuasiveness assumption, persuasiveness constraint. It's a constraint for the policy. So this constraint is an integral equation. It involves the integration with respect to the prior distribution, which is not known to the sender. But we are only able to sample to collect sample from the prior distribution. It's stored in the data. So how do we ensure persuasiveness constraint is satisfied? What we are going to do is to use a pessimism approach. That is, instead of estimating the prior distribution directly from the data, we also construct a confidence region for this prior distribution, which contains the prior distribution with high probability. Then in our policy update, we update our policy by letting it to be persuasive for all the distribution within the set of confidence region. So here, the confidence region is denoted by this BT, and it can be computed, estimated, say, using confidence ellipsoid, or using a total variation ball, total variation distance ball from centered at the empirical mean. Then we update the policy using the greedy policy with respect to the estimated Q function and subject to the persuasiveness constraint. Here, this persuasiveness is with respect to all the distribution, all the candidate prior distribution within the confidence region. Then, and this Q function is optimistic estimate of the optimal Q function. And it's to estimate this is similar to classical reinforcement learning algorithm like UCB, LSVI UCB, or other optimistic reinforcement learning method. And this this mu-t is the center of the confidence region. It can be estimated, say, using some ridge regression. And the confidence region can be constructed using confidence ellipsoid. Then with this pessimism approach, we can ensure that with high probability, all the policies satisfy this persuasiveness constraint with high probability. And more importantly, what is the price paid for achieving this pessimism? We can show that in terms of regret, there's an error term shows up due to pessimism, and it's upper bounded by the distance, well, essentially by the width of the confidence region in terms of total variation distance. And this result is obtained assuming that the prior distribution satisfies certain regularity condition. The regularity condition intuitively means that every action can be optimal action with some margin and with constant probability. In some sense, that means each action can be persuaded. Because just consider a Bandit problem. If there are some action you will never let the receiver to take, then there's no way you can explore this action. So this regularity condition essentially means that all possible action sequences can be persuaded. And then in terms of algorithm design, what I haven't talked about is how to construct this Q function. So for Q function, it's quite standard. It's constructed using it can be constructed using any optimistic reinforcement learning algorithm. And in our paper, we use LSVI UCB. So it contains two steps. The first one is to solve a ridge regression problem. And then the second step is do some uncertainty quantification and add the uncertainty and use the width of the uncertainty region as a bonus function and add it to the value function, construct an optimistic one. And as for theoretical result, we proved that first our theoretical results involve two aspects. The first one is that this algorithm ensures persuasiveness with high probability. And the second one is that it achieves a sublinear regret. And here in the regret bound, the first term is the same as the standard LSVI UCB paper. And there's additional term P0 and D, which comes from the regularity assumption of the prior distribution. And in the tabular case, that is the number of outcome and state and action are finite, we can also have this more explicit formula. And in terms of proof technique, here our additional ingredient is just the persuasiveness constraint. And in a proof, we derive a new performance difference lemma that are tailored to this persuasiveness constraint, and it can decompose the error into a few terms. And there's a term which only involves the persuasiveness, and it connects to the informal result I talked about, which is the price paid for ensuring persuasiveness. And in the interest of time, I will stop here, and thank you all for your attention.
Cool, thanks a lot. Very interesting stuff. So let's see, are there any questions right now? Oh yeah, Kostas.
A very interesting model, this Markov persuasive process. I was wondering, like, if like in the background you presented, the sender knows the prior. So I wonder if in your case the sender knows the prior, can you and it's a centralized problem, can you compute the optimal policy in polynomial time?
Oh, sender doesn't know the prior. Sender can only sample from the prior.
No, in many cases, though, I mean, the sender can see both the outcome and knows the prior. I mean, this is, I believe, even the model you started with, right? I mean, in the non-Markovian, I was wondering if the sender has this extra knowledge, like if the prior is common knowledge to both the sender and the receiver, right? But the sender also sees the real state of the world. Can you compute optimal policies in polynomial time?
Yes, because here, if you know the prior distribution, then you will just have a deterministic constraint, and with that constraint, you can use linear program to solve the policy update, so it can be computed efficiently.
Let's see, were there any other questions? I guess if you thought about like general function approximation at all?
Yeah, the proof is very modular. So as long as you can have an optimistic Q function and you know how to quantify its answer, and you can do it.
Cool. Let's see, any other questions? All right, if there's no more questions, we can go ahead and stop there.
Thank you.
We're a little over time, so why don't we maybe take like a short 5-minute break, and then if people are interested in the open problem session, we can come back and do that.